Good morning, guys. Welcome to another episode of Xa Talk Show. Today is 2020, January 11th, Saturday, 3 o'clock in the afternoon, San Francisco time. Good morning, guys. Outshine, Zumwelt, and Israel, and Justin Scoffy. And we have one ton of things to talk about. I think the main topic today is supposed to be mathematics because we have a scheduled. We have Linux config. Okay, so let me show you. Okay, so talk show here. So supposedly this is a schedule we have set. You go to my Talk Show page and you'll see it. Okay, Monday Emacs, Tuesday JavaScript, and so on. So today is Saturday, so we're supposed to talk about math. So therefore, we will talk about math. But let me do some digression. So okay, so what topics you guys like to see? But anyway, so what I'm saying is that we're gonna talk about mathematics is the main topic, and today's talk show. So let me show you today's talk show. I want to talk about several things, so many things. So first of all, let me show you my breakfast, and this is my breakfast. Okay, this is nutty bread with cheese, milk, honey, and coffee powder. And that's my keyboard, and that's my new mouse. This mouse that we're gonna talk about. Okay, so today I'm gonna show you like 1,000 things. So you can see my desk, you see, and that is the Logitech G600 mouse. Okay, so we have this is blue Windows setup, Windows shortcuts. It has like 20 keys. Stupid camera. Hold on a second. Let me get this right. Okay, so it's kind of clear. What? Shit. It's kind of. Hold on a second. So let me move here. So here. So you can see those are you. Then this is Linux setup. So Mac, it's red. Okay, stupid camera. This Logitech worst camera on earth. Blue is Windows, and white is for Linux. It's annoying between Macs and Windows because on Windows it's Control C, Control V for copy and paste, but on the Mac it's Command C, Command V for copy and paste. So if you want to program a key to switch, to copy and paste, you have to have a Mac profile and Windows profile. Very annoying. Triple, you see, triple boarding balls. Zimwell says, okay, Zimwell is here for the cellular automata, so we shall begin that, because I was going to have 1,000 things, then we're gonna never get into the topic. So let's begin with cellular automata. Okay, it's a game of life, which is a fantastic subject, and you programmers will be interested about it. Okay, so mouse, we're gonna talk about that later, and so I'm gonna show you the photos first. My photos. So this is the hall I'm in. this desk. We're gonna begin on cellular automata in a minute. Okay, but you see the hall I am in. So this is my desk. Okay, this monitor is connected to a old PC. Okay, that PC hasn't been turned on for over 2 years, and that PC is running Linux. Linux, guys, the things you love. And so that is my photos, and then the overview, and you can see the Kinesis foot pedal, which I did a video on this keyboard, on Kinesis keyboard, on the Logitech mouse, both of them, the spin wheel mouse on my right hand, and I did the video of that. And this is yesterday's lunch or something. And that mouse is a cheap Chinese mouse. So okay, that's about the photos. So let's get on to the cellular automata, the fantastic topic. Good morning, Cool for School. Controlled chaos. Yes, controlled chaos. Okay, cellular automata. So let's begin with that topic. Let's see. Let's see. So, game of life. Now, do you guys know game of life? Now, have you played Zumwalt? Have you played game of life? Game of life. Actually, I wanted to show you. Let's go to Wikipedia. Okay. So, have you played game of life? Zumwalt. Answer that, please. So, game of life. It's a fantastic, fascinating subject. Okay. So we're gonna talk about that and cellular automata in general. And these are some of the things people bought for my Amazon links. So this memory stick, not interesting. I'm gonna close it. Okay, it's $219. What is this? Sabret Rocket Q 2 terabyte. Oh, PCIe internal SSD. Oh, okay, so it's a storage solid state drive, 2 terabytes, $200. No, I'm not interested. No, but I'm interested about Game of Life. Oh, okay, you haven't seen it. Jesus, Game of Life. Good morning, Kathy. Game of Life. I played for several years in the 1990s. Remember this is 1990s. Computers are not as fast as today, but I played Game of Life for several years, and so did many mathematicians and programmers play Game of Life. And the game of life it's a thing. It's a thing that you learned how you actually visually see, you understand how deterministic things does not imply predictability. This is seems like a contradiction, like a paradox, because you might think, oh, it's deterministic, like deterministic means you have a simple rules like a programming. Like when you write a program, it's all deterministic as long as you don't have random numbers. Well, even the random numbers in programming languages, pseudo random numbers, they are also deterministic because they repeat. So when you write a program, let's say C, JavaScript, or Python, whatever, it's all deterministic, but however, it's unpredictable. You see, that's a puzzle, because how can it possibly be unpredictable? Because you code, the CPU, the logic, the motherboard, the CPU, all it's by logic. It's all deterministic. Your program flow, but however, it's unpredictable. Why? Because the simple okay the one single word to say why that is the case is because complexity. Okay, so deterministic things are very simple. No, I don't. No, not artificial randomness. I don't know what you mean by that, but okay, let me. What I'm saying is that so things are deterministic, but when you involve so much computation, it takes billions of years to run. You cannot predict what's the outcome, because the only way to predict it is to run it, and you will see that demonstrated in cellular automata. But let me show you. Okay, so let's start to talk about cellular automata. I was just going to show you some of the Amazon stuff. So let's begin with cellular automata. But I want to get on to Discord first. So cellular automata. Okay, give me a second. Discord, yay! So if you have not already joined Discord, okay, cellular automata. So let me show you cellular automata. So this is cellular. This is game of life. Game of life is one of the cellular automata. Okay, you look at the pictures on the right. Let me show you some demo. Okay, so actually, so let's go to best game of life. Okay, actually we jumping a lot. We jumping all over the place. So let me try to follow some kind of order. So game of life is such that you begin with a grid. Okay, let me show you a grid. Just a rectangular grid. And on this grid, you can have each cell, each cell in the grid. It can be either black or white. Okay, then each cell can be black or white. Okay, you begin with a empty grid, then you start with some cell, black cells, either random or whatever you want, everywhere you want. Then that you say that's the first generation. Okay, so the next generation, you see, let me show you. Okay, you see how these things, look at the picture over here. You see how those things kind of moves. Uh, you see how those things kind of moves because you go by generation. So let me get back to the generation again. So you begin with a grid, you put some dots on it, then that's called the first generation. Let's say the first second. Okay. Then the next generation, the second is that you determine, it follows a simple rule that tells you which cell should be colored, which cell should remain blank. So the rule is very simple. Let me tell you the rules. Okay, you can also go to Wikipedia and watch it. So let me. So they have some. You see, they made some of these animations to show you. And let me show you this one. Okay, this one is a game of life on a on a knot. This knot is called trifoil knot. You see those dots patterns, they move. They move according to very simple rules. Okay, so let me tell you about what are the rules. So sounds can be modeled by stochastic process in lower dimension. No, well, stochastic process is a random process. That's a different topic. This thing is not random. This thing is fully deterministic by a simple rule. So let me tell you what are the rules that creates these moving things. What are the rules that creates these moving things? Let me tell you. So we go to Wikipedia. You can read Wikipedia. Very simple. So let me just read. So here are the rules. Okay. Uh, 4 rules. Okay, so it says, let me read it. Any cell with fewer than 2 live neighbors dies as if by underpopulation. So you have cells. Let me show you. Okay, so let me open this. So this picture, this grid, each point on it is called a cell. So for each cell, you have like 1, 2, 3, 4, 5, 6, 7, 8, 8 neighbors. The neighbors surrounding the cell, whatever cell you are thinking. So each cell has 1, 2, 3, 4, 5, 6, 7, 8, 8 neighbors. So let's get back to the rules. Uh, let me read the whole thing. The universe of Game of Life is an infinite two-dimensional orthogonal grid of square cells, each of which is in one of 2 possible states, alive or dead. Okay, alive is black, dead is white. So another way you say it's populated or unpopulated. Okay, so every cell interacts with its 8 neighbors, right? So if you have a cell here, you have 1, 2, 3, 4, 5, 6, 7, 8, 8 neighbors. Okay, um, which are the cells that are horizontally and vertically and diagonally adjacent, neighbors. At each step in time, the following transition occurs. So these are the rules, these 4 rules. So if a cell has fewer than 2 live neighbors, then it dies. Okay. If a cell has 2 or 3 live neighbors, then it lives on the next generation. Okay. If a cell has more than 3 live neighbors, then it dies again. A dead cell with exactly 3 live neighbors becomes alive. Okay, so here are the rules. So in summary, if a cell, if it has two, if a living cell, a black cell, if it has 2 or 3 live neighbors, then the next generation that cell remain alive. Okay, but if it has fewer than 2 neighbors or more than 3 neighbors, then it dies. In the next generation, it becomes white. It becomes empty. So that's a rule. And also, on a empty cell, if it has a dead cell with exactly 3 live neighbors, becomes a live cell. Right. So a empty cell, if it has 3 black cells as its neighbor, then in the next generation it becomes alive. It becomes black too. So these are the rules, very extremely simple rules. And they create things like that. They create a pattern like that. So actually, I should show you. I should demonstrate a live uh, JavaScript app somewhere. So let me search it. Okay, so game of life. I want to have a applet. Game of Life, download game for Windows PC. I'm gonna show you the best programs for it. Okay, so don't rely on these random websites. These are mostly, I think they are garbage websites created by Facebook and Twitter. They commercial, ad spamming garbage information, garbage websites. But I want to find you. So does anyone know a good JavaScript website that shows Game of Life? Uh, I want to show you a live demo. So, but anyway, this is a Game of Life on Taurus. Now remember, the thing to remember is that how they move is all deterministic. So it's extremely fascinating. You see, by these simple rules, then you have this pattern. It seems to have a life by itself. It have a life by itself. And so game of life, this kind of thing, this game of life, this is called cellular automata. Why is it called cellular automata? Because it's cells. It's just cells. And why is it called automata? Because automata is a traditional term for machines that run by itself. So that's why this is called cellular automata. It's cells, and it just run by itself. It just appears to, have a life of its own. And the game of life we just described, this thing is one of the infinite number of cellular automata. Okay, so these are all cellular automata. So that's why I'm talking about cellular automata today. And game of cell is one of the most well-known cellular automata. And let me show you. We need to actually run a application to show you how. You have to see it. You have to see it to believe it. So for example, on Wikipedia they show this one. Now this one is based on hexagonal grid. So then you have different situations. You have you see different patterns emerging. So this game of life originally is trying to model population. They are trying to Conway, this guy John Horton Conway, very well known mathematician. John Horton Conway, this guy, he's a British guy. Okay, so yeah, I'm going to show you great softwares, to run these, the greatest one, because I've been watching this scene since 1990s. it's a big, it's a huge science topic. It's a fad. I mean, it's been very extremely popular among basically all scientists and mathematicians. Be, so originally it began as a model started by this John Horton Conway. They trying to find a model to model population growth, and also some theories about population growth or die out. Population, it may grow or it might die out, become a ghost town, and everyone dies. So they trying to model it by certain mathematical rules, and there are many theoretical questions about population growth. So, for example, is it possible? One of the questions originally about game of life, with these specific rules is that, so is it possible to begin with a pattern such that then the population will grow infinitely? It will just grow and grow and grow, then grow forever. Is it possible? That's one of the questions. And do you know the answer? You don't know the answer. You have to actually play it because you see, by this simple rule. So let me repeat. So you start with a blank. You start with a blank universe. The grid. Then you put some patterns on it. Doesn't matter what pattern, but let's say one dot. Okay, if you have one dot in the next generation, it'll die because it has no neighbors, and when it has no neighbors, according to the rule, it dies. So you become empty, then it's dead. So one cell is not interesting, but if you put two of them side by side, the next generation will also die out because each cell has one neighbor, and when you only have one neighbor, you die. So so you become dead again, becomes all white again. So, but if you have three cells, let's say we arrange them in a horizontal line, that start to become interesting. Then you start to have this pattern. This one called blinker. You see this one? Because so for the cells on the side, each one of them has only one neighbor. So in next generation they die. But however, the one in the middle, it has two neighbors. So in the next generation, it stays alive. The one in the middle, it stays alive. Now, however, the empty ones, on top and bottom, each one of them has three neighbors. So in the next generation, they become alive again. So you begin with a three dots horizontally. Then next generation, they become three dots vertically. Then they just flip. They just repeat forever. So this becomes a stable population. So when you have a three dots, it just flips. It's called each pattern. We have given them a name. So this pattern is called blinker. And then, over the years, so this is a verdant. This is a verdant field to approach. You can play game of life, just get out a piece of grid paper and draw it, but that's very tedious. You really need to do this on a computer. So great programmers, tons of professional programmers, amateur programmers, and greatest programmers, they have dived years into writing this program and trying to make efficient. So, for example, one of the very well-known game of life programmer is this mathematician whose name is somewhere here. I don't remember offhand, but his name is he lives right here in California. His name is a great mathematician. Okay, so he's one of the great programmer. One of the greatest programmer in the past 100 years. What's his name? So his name is, I'm sure I can find his name. Just give me a second. I need to remember his name. He is also one of the original lead programmer for the computer algebra system called written in Lisp, Maxima. yeah, maximum. Was it maximum, or do you guys remember? I can't remember the names, but we'll get there. Okay, so so many references. I'm pretty sure one of them is this guy, because he not only, he devised some of the most efficient algorithms and data structure for game of life, and also he discovered many of the game of life's patterns and theories. So there are tremendous theories about game of life, about cellular automata in general. For example, one of the question is, uh, one of the question, for example, is reverse game of life. That is, given a pattern, let's say you draw some random cells, so is it possible for this pattern to ever occur? That's a question. So in order to figure that out, you have to trace back, you have to find a pattern that becomes that pattern. Is it possible? So that's one of the questions. So there exist patterns that can never happen, and this is called, anyway, there are many jargons and names for, then, so eventually, after 10 years, 20 years, even today, it's still going. We have many patterns, named patterns. We have spaceships. These on the right column is called spaceships. What they do is that they'll just move. Okay, they just move, and it's a big thing. You can play with this and dive into for a month. Every day you spend an hour a day and dive into study, all the jargons, what they do, the speed, the movement. You can study it for a month at least, but many of us spend years, doing this because, for example, these are called spaceships. Okay, so what's the interesting thing about spaceships? What they are is that they become a pattern that will move on a grid. In the next generation, they become some other shape on a grid, and next generation they become some other shape on a grid. Eventually, they become themselves, original shape, but in a different position. So they just move. So this kind of patterns is called spaceships. So once you discover the first spaceship ship discovered is this one called glider. The hacker guy, ESR, Eric Raymond. Remember, he created a hacker's logo. That is this one, spaceship called glider. Okay, this is the first spaceship discovered. Now, once you discover spaceship, you answered one of the most original question about game of life. That is it possible to have a pattern such that it grows, the population grows infinitely? Yes. To create that, all you have to do is to create a pattern that generates a spaceship. So these are called spaceships. How do you generate a spaceship? Then you have patterns that will generate this spaceship infinitely. Let me show you. Okay. For example, this one. Okay, this classic, this picture. Let me magnify. Okay, you cannot magnify much. So you see so the pattern on the top row, that pattern is called a gun. So generation after generation, it creates this glider. So that pattern is called a gun. Now we call it a gun. So that pattern is called a gun, and this gun just creates this glider, and this glider just shoot out, infinitely forever. So this answers the question that it's possible to have a pattern such that it creates, the population grows forever. So once you have, this is fascinating because once you have this pattern, this gun, you can play with it. You can play by creating several guns, and the the gliders shoot at each other. Once they meet, they become some other pattern. Then you don't know what will happen. Sometimes they grow so large, like the explosion, they kill the guns, they destroy the guns you have. But sometimes not. Sometimes they die out. So it's very it's incredibly fascinating. So actually, to actually see that, I need to show you some kind of interactive application. Um, these days I haven't been following this for the past 10 years, so I don't know right now what is the best website that has Game of Life. I've been following this in 1990s and 2000s, but not in the past 10 years, so I don't know. I know there are tons of websites that has these, but the point is you want to find a good one. Does anyone of you know? Okay, so these different life forms grow organically from the initial cells. Yes, exactly. So, and there are so many theoretical questions about it. So one of the things I learned this in 1990s is that once you play this, okay, you need to find a JavaScript. I'm gonna show you the programs. Okay, let me show you the programs now. This one is what you want, Golly. Okay, so so actually, hold on a second. Let me sync my website so you can go to my website for the files. Okay, so copy it. Paste it. So you go to that link, then you'll find my link about the best programs for Cellular Automata you can download. Now this one, Golly, has been around. This guy, Andrew Trevorrow, he's been writing programs since 1990s. So he wrote the best. Okay, I know because I surveyed all of them, all cellular automata programs on the web or on the Mac or on Windows. I know them all in the year 1990s and early 2000s. I've tried every one of them. So this Andrew Trevorrow guy, he started to write this Game of Life program since 1990s, and his is the best program. And then in 2002 he started to port it to Mac OS 10. Mac switched from Mac OS to Mac OS X, Unix. So anyway, this is the best one. Okay, check out this Andrew. You go to my website and you check this one out called Golly. So why is it? There are so many interesting things about Game of Life. I want to show you. I want to show you a real game in process, because without actually showing you, you don't get, like animation is worth a million words. You don't get what exactly is a deal. But once you see it, once you see these almost randomish, remember they are not random at all. There's zero random thing going on. The rules are very simple. It's deterministic. So you can run this for a million generation, for a billion generation, for gazillion, trillion raised to the trillion billion power of generation, peta generation or whatever. Infinite. So the question is, so you have this very simple deterministic thing. But however, let me ask you, for example, if you are given this pattern, what will happen in, will this pattern die out, or will this pattern become stable, or will this pattern grow infinitely? One of three choices. Will they die out, or will they become stable, like the population doesn't grow and doesn't shrink neither. It becomes one of those blinker pattern, stable. or will it, grow and grow infinitely? So that's the question. Given a pattern, what will happen to it? Now before game of life, before cellular automata, you might think, oh, it's all deterministic, obviously, so we can predict, because we just follow the rules. But the problem is you have to follow potentially trillion, gazillion trillion, more than the life of the universe times to know the answer. So yes, it's in a sense it's deterministic. You can predict it in a sense, but by the time you predict it, centuries, eons, the Earth will be already dead. So that's the thing. The only way to know the future is to compute it, is to live through it. That's the thing. So this relates to, this theoretical thing relates to many philosophy in real life as well, because in real life we have the question of will. Do we actually have power of will? And what does prediction means? So this touches or answers many of that questions in part. At least one thing we know is that deterministic systems may not be predictable, because then it opens the question of what does prediction mean. If we can predict, what does prediction mean? It opens that question. So I mean, if you follow the game of life, the cellular automata, then you will see, we humans, we are, physically, there's atoms and quarks, or whatever, quantum mechanics. Anyway, that's getting complicated. So that's about that. Okay, so I want to show you. So okay, you go get that programs. Okay, and there's another thing I want to show you. For example, this one. This one is someone. Stupid. Someone created a cellular automata on a hexagonal grid. She is a student of computer science. Okay, so I'm showing you this example as a different cellular automata. So you can see she's running this on a. Okay, let's open it. Let's go to CodePen. What happened to CodePen? Currently offline. Oh, CodePen is down. Jesus. Let me show you. Okay, game of life JavaScript. I want a page where you can run game of life on a website. Am I still on? Okay, so that's any questions, comments? So if you guys found a good website to run game of life, let me know. Okay. I mean, obviously there are many apps for phone. Jesus, they are all for phone and stores. Jesus, these apps and Apple stores and Android, Google stores. Fuck. So let's JavaScript. Let's say online, Game of Life online. There it is. Play on Pokey. I don't know what kind of thing is this. Jesus, play on Coke. This is probably not what we want. I can tell because all this garbage, these pop garbage icons on the side. This is a garbage website. Yeah, I don't want this. You see these websites, when you read their title, you can tell what's their nature. You see this play the game of life, a free online game. When you see that kind of wording, it's crap. It's just a garbage website. Okay, this is promising. John Conway's Game of Life. Let's open that. Okay, there. This is a good one. Looks like, yeah, this is a good one. So let me begin. So let's say we start with this pattern. Okay, let's start. Now that shows the evolution. Okay, this looks like this start to show an evolution of it. What is this? Clear glider. Okay, this is not interesting. Stop. And we need to run this faster. Okay, so you can go to the next generation. You can click, go to the next generation, or you can just let it run by itself. So that's Game of Life. So you can see, okay, wait. So you see those things, those are called beehive. Those are stable patterns. Bloat and more bloat, yeah. So anyway, that's a Game of Life, and we want to make it go faster. So you can play this for just for hours and for years, and then today as computer becomes so we I this began in 1990s, and okay, so right now it reached a stable position. You see the generation. You can see the generation on the lower right corner. It right now it's 800 and still going, but the generation, but the pattern becomes stable. They don't change anymore, because if you have this pattern, by the Game of Life rule, the next generation they remain the same, because for each cell you have three neighbors, so that means the cell remains alive and nothing else changes. So those are the stable patterns. These three is called beehive. This square is called I forgot what's the name. Block. Okay, so the square is called block. And so once you study, so there are actually a website, encyclopedia or wiki of Game of Life. So you go there, you have thousands of patterns. It's all discovered by people. They don't, these things. Now we look at them, you see it's all there, but we don't know before. So it's discovered every year. So next 2 years you discover something new. For example, once you have spaceship, you want to measure how fast the spaceship moves. So they have, so in the Game of Life, they have jargons. They called speed of light. Speed. When you have a spaceship that moves at speed of light, that means for every generation, it will move itself. In every generation, usually, nothing typically in principle, nothing will move that fast. So they created this jargon's speed of light, similar to the real world speed of light. Basically that's impossible because many of these spaceships, they move by like every 5 generations they move how certain number of cells. So you divide by the generation, the number of cells it moved divided by the number of generation it takes to move there is the speed of a spaceship pattern. So you can read Wikipedia, and there are wikis and encyclopedias of Game of Life. And there are still unsolved questions, quite a lot, very theoretical questions. And one of the thing, let me show you another thing. This Game of Life and Cellular Automata in general, it's part of theoretical computer science. Okay, like you guys programmers, you may not heard of it. This is actually part of theoretical computer science. And I wanted to say, yeah. So one of the fundamental question about this cellular automata is about Turing machines. You guys probably heard, every nerd, every idiotic nerd says Turing machine every day on Hacker News, on this blog. Every nerd is like, oh, Turing machine, Turing machine, oh, lambda calculus. They don't know shit. Now, Game of Life is one of, cellular automata is one of the model of computation, like Turing machines. Okay, Turing machine happens to be, becomes a drama kind of thing. Every nerd is just repeated Turing machine, Turing machine, Turing my ass. Turing machine is the most idiotic, most ugly model of universal computation. Okay. And also because Alan Turing, because he's a gay and he ate the apple poison, things like that. So it's drama. It's by these idiotic computer programmers like the Haskell people, Haskell and Unix people, Linux people. So anyway, cellular automata is one of the model of universal computing machine, like Turing machine. Okay, they are in the same category, same nature. And one of so there are a lot of theoretical computer science questions about it. And I want to show you one of the uh, yeah. So universal computers. So the question is, can you model a universal computing machine using cellular automata? The answer is yes. But another question is, can you model universal computing machine using Game of Life specifically, using this specifically? And the answer is yes. We don't know the answer until I forgot when, like 10 years ago or something. We then we computer scientists, they publish in journals. Then they publish, oh, we discover this pattern that can model that is a universal computing machine. And to do that, what you need to do is basically you want to find a pattern that emulates logic gate, like the OR XOR gate. So let me show you some of the interesting things. Okay, so anyway, you have to play this with this. Okay, let me clear a bit more and show you. Glider. Okay, I don't care about glider. Clear, stop, clear. Okay, so I'm going to create a random patterns. So the question is, you have to predict what will happen to this pattern. So let's start. Okay, so there's one glider going off. Oh, so it's stable. This is not too interesting. So one of the question is, can you have the least number of starting cells, and and such that it grows to the most number of population, like or never stops. That's the question. So one of the pattern we already know, a record, is one of the, I don't know if they show it here. Here, these are polynomial. Okay, this pattern. The simple patterns people have already exhaustively tried them. You begin with one cell always dies. You begin with three cells, two, then three. So people have exhaustively tried, the low number up to, I don't know what, 10 or 13 or something cells possibility. But you can see how this is computationally intensive, because basically you have infinite number of patterns, and you want to know what they will become. You don't know. The only way to know is you have to run it. So let's try this R pentomino pattern. Okay, let me do that. Let's try that. Clear. So okay, so let's try that. And start and shrink, shrink, shrink. This will run a long time, like thousands of generation. I mean, you might have to wait for 5 minutes or 10 minutes. It will run for a long time. Break the loop. Hey, break the loop. Break the loop. I think I know who you are, right? Yes, you haven't been here for a long time. I was wondering, where have you been? Break the loop. Break the loop says, is it a misnomer that the game of life is called a game because it is not a game in the board of video games? Yeah, in a sense, game in a general sense. Also, hello, Xar. Long time no see. Yes, indeed. I was wondering, where did you go? I was, thinking of trying to contact you on Twitter, but I checked. Actually, I checked like last week. I think you are not active on Twitter. So, anyway, great to hear from you, and Happy New Year. I have not gotten into Dwarf Fortress, but have friends that do, and they have fun stories. Dwarf Fortress, what is that? Okay, anyway, this pattern died. Stop. So anyway, so that's about Game of Life. You can see it's very computational intensive. So this web-based thing is not that fast. You see, because once you seriously get into it, you'll have a universe that's millions of cells going on. You really, the faster the computation, the your CPU or whatever, it'll help. So that is why I recommend you get this program. This is pretty much one of the fastest. Okay, golly. I mean, also this is a great programming exercise. Okay, so you can go and write your own game of life in JavaScript, in Java, in Golang, in C, C++, in Nim, whatever language you like. You can write it. But however, don't hope for that. Your program will not be good, because people, computer scientists, they have dived into this so much that they have devised, the best algorithms and the best data structure for this. How does a game of life simulate a computer? So what you have to do is basically you want to create a logic machine. How can I explain it? Let me see. Remember, you remember, yeah, let me tell you. Okay, so abacus. Okay, let me show you abacus. You know abacus, right? So here we have some pictures of abacus. This is Chinese style, old Chinese style. Nobody uses this style anymore. And this is Japanese style abacus. So abacus is actually one of the it's you can call it a universal computing machine. You have bits, you move their positions, and and it follows certain rules, algorithms. So this is actually can be a model of a universal computing machine. So basically, if you want to model, if you want to have some model of universal computing machine, uh, there is a technical way to how that is defined, but I'm not going to go there. I'm not. There's a technical. It's really actually it's not easy to understand. Basically, the way people do it, if you are a mathematician, if you are a real computer scientist, professor in computer, if you want to publish a paper, one way to do it, create a universal computing machine, is to demonstrate that your model, your machine, can emulate Turing machine. Okay, that's the most common way. In other words, you want to create a system that can emulate known universal Turing machines, and this is the most common way to prove that you indeed have a universal Turing machine. Now, but what's the exact definition of Turing machine without relying on some existing Turing machine? That question, actually, I'm not I cannot answer that. Okay, but anyway, but I can tell you how I can give you the idea of what it means to create a model that is a universal Turing machine. Basically, you can, for example, you can emulate a calculus. I mean, a abacus that will do. So anyway, let's skip that question. I don't know how I don't know the answer. I don't know how to that answer that. That's a very interesting question because I really wanted to know that, but that's not a trivial question. You have to read a lot, and usually it's difficult to read. So, but only of those people who have really know this stuff well, they can explain. Uh, and don't listen to any of the programmers. They don't know shit. Okay, they have 20 years of programming. Doesn't matter. It's Haskell. They cannot explain. And also, or whatever they explain, it's misleading shit. Okay, so don't listen to any of the programmers. If you want to know the real answer, you can start to read Wikipedia. Universal machine. Okay, so you go read Wikipedia. They have definitions. I can actually, if we read Wikipedia, I can kind of interpret. I can explain what it is. Universal Turing machine. Okay, blah 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 blah. Introduction, stored program computer, mathematical theory. Okay. Um, Examples of universal machine coding. Okay, and programming. Yeah, they don't. Yeah. So anyway, you have to dive into this. This is a you know this is a post. This is a graduate level programming computer science. Okay, so if you are a computer science student, you go to university, you get a degree, then and you wouldn't know, you wouldn't be able to explain that. That's the context about that. But however, it's not that difficult though. You just have to dive into it a lot. But I want to show you some of the interesting things. And that'll be it for today. Okay, so yeah, let me mention this. So Stephen Wolfram has written this book, A New Kind of Science. Let me show you. My stack of books, heavy math books and stuff. And let me show you. A Conflict of Vision by Thomas Sowell. This is one of my favorite author, Thomas Sowell. The Expose keyboard, fantastic. An Elementary Introduction to Wolfram Language by Stephen Wolfram. He sent me the book 3 years ago, 5 years ago or so. Theory of Sets. I had this book since 1990s. It's that's Theory of Sets. And Groups and a Path to Geometry. I don't like this book. Actually, come by. If you guys, the things I don't want, I throw them away. So you guys can have it. I don't have money, but you guys can have the books I don't want. You see, I don't like that book, but you may like that book. Because the book writing style, it's taste and different people. So this I talked about this topic before. This is patterns, tilings and patterns. The professor sent it to me in 1990s. This professor, tilings and patterns. This is a classic book on. This is the encyclopedia, the Bible of all theories, math theories about tilings and patterns. This book, a friend gave it to me. Huang, okay, he gave it to me. I haven't read it. It's understanding computation in Ruby. So they use Ruby to have code. I haven't read it, but I don't think it's not. I just read Wikipedia. And here is Stephen Wolfram, A New Kind of Science. This is heavy, big door stopper. Okay, great, fantastic pictures. Detail in detail. This book just for the illustration, it should win an award. But it's not winning an award because all the scientists don't like this guy because he's a braggadocio. That is why he's not winning awards from these inferior scientists. He thinks he's the greatest scientist, you see. A New Kind of Science. This entire book is about cellular automata, the things we talked about. And I have a annotation on this entire book. The Crucial Experiment, The World of Simple Programs. I read that book like twice. System based on numbers. So anyway, this entire book is about cellular automata. And Stephen Wolfram, he happens to be a nutcase. He's a nut job. He's very highly, he's very into it. He believes that the universe is actually a cellular automata, and he's a genius. Okay, when he's 17 or something, he won the MacArthur's Award, Genius Award. And when he's 15 or something, he got a PhD from Oxford or Cambridge, something like that. He's from UK, and he created Mathematica when he's 20 something, and he become a entrepreneur, running Mathematica and successful. And when he's 20, 17 or something, he's a theoretical physicist, publishing papers in physicist journals, quantum mechanics or whatever. That's this guy. And he's a big he's one of the pioneer, or the possibly the greatest expert on cellular automata, and he believes he's also a nutcase. Okay, because he believes the universe is kind of modeled on cellular automata, some things like that. Okay, so you have to. So that's my notes and opinion about that guy. And so let me show you one more thing. Okay, two more things actually. So one of the things I want to show you is game of life recursion, and the other one is jargon automata in finite state automata. Now, if you are a programmer, you might have heard of automata, and you might have heard finite state automata. Especially if you study compilers, you will have heard of that, because yeah. And why automata? Because, like I mentioned before, automata and cellular automata, they are kind of the main topics in theoretical computer science. you know by the way, you don't hear about these things in average programming community. In programming community hackers, you hear about Linux man page, Unix, Linux, or small is beautiful, Unix philosophy, or tail recursion, or Haskell monad, or category. Those are crap. Okay, those are the most fucking idiotic shit. They telling you about. That's what you hear every day. That's your brain. If you are that's why sometimes I flame programmers, and many of you, many of my followers think, oh my god, Sa is a weird guy. They're very weird. But I'm trying to show you why that is the case, because I'm trying to give you some examples why I said is true. Okay, maybe exaggerated, maybe in a dramatic way, but it makes sense, because you don't hear what I'm talking about. Today, for example, the topic about computer science, about theoretical computer science, about cellular automata, about what does it mean, a universal Turing machine, not just Turing machine. Okay, we're talking about universal computing machine, and about automata. This you don't hear. You don't hear in the hacker news. These fucking computer programmer, fucking idiots. Every day they are like vi vim. Haskell, parallel. The something. They are jargons. Object-oriented programming patterns. These fuckheads. Meanwhile, you don't. When I talk about these things, okay, it's like, hey, what is that? You never heard of. That's the thing. You see, that's a difference. That's the difference between the programmers community. They are not doing any computer science at all. They are just drama. Okay, I digress into a rant. So I wanted to show you the one more thing. Okay. Oh yeah. So about the jargon's automata. That's a very interesting story, because automata, this jargon began about 2,000 years ago in the story of Europa and the bull. Okay, so I talked about this in one of my videos before. Europa and the bull. Let me show you there. So this bull, and which is the foundation of Western philosophy, Western society, Europa, and the bull. Europe is named after her, Europa, and the bull is God, the Zeus, the omnipotent, the all-powerful God, and he seduced or raped Europa. Okay, so that is why the word rape is on every white guy's mouth every day. Rape, 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 rape. This, that. Rape, rape every day. Their brain is filled with it because this is part of the foundation of Western society, the philosophy, their train of thought. They don't see anything else. They just see justice, justice, rape, and this thing. That's the foundation. So Europa and the bull, and you have we have several of these artworks. It's fantastic. Okay, fantastic. And okay, let me tell you the story. So how it relates to automata. So Zeus, the all-powerful god, he saw this pretty girl, young, of course, young girl, pretty young girl, lovely, beautiful. So the Zeus wants to fuck her. So Zeus changed himself into a great, giant, beautiful white bull. Okay, and he just go to the girl, like like trying to do nothing, and the girls, then girl being girls, oh my God, beautiful bull, and she tries to start to pet the bull. So that this is the story of the seduction of Europa by Zeus, the god, the all-powerful king of all gods, Zeus. So then the bull just run off. The once the Europa hopped onto the bull just run off, and Europa is like, oh my God, they cannot get off. So there are poems about it since like 2,000 years ago, 43 BC. Okay, so here's a poem describing the situation. Okay, so let's see. How long have I been talking? Okay, we are losing audience quickly. So it says, and gradually she lost her fear, and he offered his breasts for her virgin caresses, his horns for her to wind with chains of flowers, and so on. Anyway, but Zeus gave her three gifts, and one of them is okay. So Zeus gave her three gifts. One of them is a giant automaton, which means a robot, and that is this thing. This coin from what era? 2,000 years ago. 300 BC. So 2,300 years ago, this coin. So that's automata, basically a giant robot. So when you see mecha today, the origin is not Japan, it's Greek. Automata, this thing, 2,000 years ago. Zeus created this thing as a gift to this girl, Europa. That's one of the gift. Okay, so let's see. So you can read about my articles. Okay, Europa. So one more thing I want to show you is recursion. Okay, so Kasali, game of life, recursion. I'm gonna show you that, and that's it for today. Conway's game of life, recursively defined. So let's go to YouTube. So let me copy that and put it in my talk show. Okay, let's go to YouTube, magnify, and watch this, and that'll be it for today. Great to see you. Great, break the loop, and there it is. You see that? That's recursion. So you have game of life that emulate game of life by itself. You see that? You see, on the surface we see, these cells, black cells and white cells, but actually that black cell is actually 1 billion cells inside it. So you have like recursion, you have game of life within a game of life within a game of life. And this is how you do, this is what it means to have a universal computing machine. Now, that's a bit hand waving because yeah, I'm not sure what I'm saying here, but what I'm saying is that recursion, this kind of recursion thing, is intimately tied with about how you can how about the definition of creating a universal computing machine. Okay, so I don't know exactly how they relate, but I do know it's like very much related. I don't know if it's one implies the other or not, but there it is, an example. So you can see recursion with, yeah. So thank you guys for watching. Yeah, when I saw this video came out in 2011, and this guy later on I learned, Mike Stay. Mike Stay is also a mathematician. He's on Twitter. He's also on Google Plus. And I've talked to him once. But anyways, so he created this in 2011, and turns out he's a student of that mathematician. I talked several times. What's his name? There's a mathematician who taught me a lot of math. Okay, I can find his name easily. Just give me a second. This guy. Okay, so this guy, John Bayes. Okay, so John Bayes is a great mathematician. He taught me a lot of things. So that this guy who created this recursive game of life happens to be a student of John Bayes. So yeah, so this is very much theoretical computer science stuff. But what's my point? Oh yeah, so this came out in 2011. Okay, and when I saw it, it's amazing. It's like it it's kind of it's send a chill down your spine. It kind of gives you a different perception of the universe. Okay, bye guys.